The next few problems on this worksheet are going to deal with the stereospecificity of the E2 reaction. Stereospecificity is something that we need to take into consideration when the E2 reaction is forming a double bond between two chiral carbons. So this is going to be when we form carbon-carbon double bond between two carbons that are chiral. We're also going to see stereospecificity is a factor when we're doing an E2 reaction on a cyclic molecule. So we're going to look at examples of that on question number 5, and then on the next page we have some other cyclic molecule problems. So this, again, stereospecificity is going to be an issue if we're dealing with elimination between two chiral carbons or on a ring, specifically on a cyclohexane ring. So we're going to start with these problems where we're looking at a straight chain and we're going to be doing elimination between two chiral carbons. And let's take a look at this first example. So initially we're just going to approach this like we would do a normal an E2 reaction. So we want to identify the carbon atom that has the leaving group. We want to also identify the carbon atoms that are attached to it, and then sort of draw in those hydrogen atoms so that we know what we're working with. And this hydrogen atom, because there is stereochemistry on this particular carbon, we want to show the stereochemistry of that hydrogen atom. Remember, if a carbon is chiral, it's going to have two straight line bonds and they have to be adjacent to each other. It's going to have a dashed bond and it's going to have a wedge bond. They have to be adjacent to each other. So we've got two possible sites for elimination here, and the direction on the left, so elimination this way, forming a double bond in this particular site, this is not a stereospecific reaction. This is not a chiral carbon. It's achiral because it has two hydrogens on it. And so this reaction here, forming the double bond in this spot, is just like all of the other E2, simple, straightforward E2 reactions we've seen so far. The base is going to grab a hydrogen, move those electrons in to form the double bond, get rid of the leaving group, and that's going to give us this product right here. We do want to make sure, that's a really bad looking bond there. We do want to make sure, first of all, that we are not making any changes to this portion of the molecule. That means we're not doing anything to the stereochemistry right here because we haven't done any chemistry to that carbon. Nothing about that carbon is going to change. But we are forming a carbon-carbon double bond in this position, and we always want to ask ourselves, whenever we make an alkene, we always want to ask ourselves, oh, is there a stereoisomer of that guy that I could draw? And there is in this case. So we want to draw those two products. We're not worrying about major versus minor at this time. And so we're just trying to get all of the different stereoisomers drawn. And so that's going to be just our traditional E2 reaction proceeding on the left-hand side. Now, I'm going to erase my curved arrows because we're going to draw the other E2 reaction. This is going to be the elimination reaction that takes place right here. Now, both of these carbon atoms are chiral. I'm going to draw the hydrogen in. Both of these carbon atoms are chiral, which means we have to think about stereospecificity. And in order for us to help predict the product of this reaction accurately, we are going to use a Newman projection. We're going to draw a Newman projection that sights down that particular bond where all of the action is going to take place. I'm going to draw sighting in this particular direction, but you could also sight it in this particular direction. And this is where having a model kit might be handy. It might be helpful, depending on how comfortable you are with drawing your Newman projections. So here I am drawing the front and the back carbons. Now I'm going to draw the substituents on the front carbon. The front carbon for my Newman projection, which is this guy right here, it has that ethyl group up top. I'm just going to abbreviate that ET. That's the CH2CH3. We have a hydrogen down to the left and a chlorine down to the right. And then on the back carbon, we have on this carbon right here, we have an ethyl group that is sticking down. I'm going to abbreviate that ET. Hydrogen up to the right and a methyl ME up to the left. Now, in order for elimination to take place between two chiral carbons, the leaving group, which is this guy right here, needs to be in an anti-configuration with the hydrogen atom that's going to be eliminated, the hydrogen atom on this carbon. So the methyl group, or excuse me, the leaving group, which I've highlighted, is currently anti to the methyl group, and no elimination can take place when it's in that configuration. So what we need to do is draw a conformer of this particular molecule. What we need to do is rotate the back carbon or rotate the front carbon if we'd like, so that the chlorine is anti or 180 degrees from the hydrogen that's about to be eliminated. I think that in order to just kind of make my life easy, I think I'm going to rotate the front carbon. So I'm going to take the chlorine and I'm going to move it into this position. The hydrogen I'm going to get moving into this position, and the ethyl group is going to come down here. And I'm going to draw what that looks like over here. So my back carbon, I didn't do any rotation, so nothing has changed about the back carbon. My front carbon, the chlorine is now down to the left, the hydrogen is up top, and the ethyl is down to the right. And I'm going to highlight again, there's the chlorine, there's the hydrogen. They are 180 degrees apart from each other. This is the conformation that the molecule takes when it does an E2 elimination reaction. So when this reaction occurs, the elimination wipes out those two parts of the molecule. What we have left on our double bond is a methyl and a hydrogen that are on the same side or cis to each other, and two ethyl groups that are also cis to each other. So Newman projection is really helpful because it helps us visualize which functional groups are cis to each other. Now, when we go to translate that into a drawing, for me, typically, I don't try to take this Newman projection and turn it into a really pretty clean line structure, at least not at first. What I'm going to do is I'm just going to draw a carbon-carbon double bond, and I'm going to say I've got a methyl and a hydrogen that are on the same side of my carbon-carbon double bond, so that means it's going to look like this. And then I've got two ethyl groups that are also cis to each other or on the same side of the double bond. And that's my representation for the third product of the molecule here. Now that, of course, is not the best looking thing. You know, it doesn't look as pretty as these guys over here, but it's the correct answer. You know, and anybody should be able to interpret this answer. If you're submitting this as like a question to a test or something, there should be no issues with that. But if you do have to clean it up and make it look pretty, if you feel like that's necessary, then what I would do is start by erasing and replacing my little abbreviations. So I'm going to be doing this in condensed notation. I'm going to erase my methyl and replace that with the actual, the ethyl with the ethyl group, and the methyl, I'll replace that with a methyl group. That looks a little bit more normal. And if you have to make it into a line structure, then you would be able to go from here in terms of turning it into a line structure. So that's a lot to deal with. Let's practice it again with our next example. First, we're going to find the carbon atom that's holding a leaving group. And look, this carbon atom has two leaving groups. That's pretty cool. We want to identify the carbon atoms that are attached to it, and we want to draw the hydrogens in on those carbon atoms. Carbon to the left, that is an achiral carbon because it has two methyl groups. So there's only one hydrogen on there, and we don't need to show its stereochemistry or worry about its stereochemistry. The other hydrogen is going on to a chiral carbon, so that's one where we are going to have to worry about the reaction. We're going to start with this elimination reaction over here on this side because that's the easy side. I'm not even going to draw curved arrows for this. We've seen this reaction quite a bit right there. Now remember, we don't want to touch the stereochemistry on this carbon because we didn't do any chemistry there. We did our chemistry here. Now, in terms of what's the leaving group in this case, maybe I will draw some curved arrows here. So I'm going to use my hydroxide to grab the hydrogen, break that carbon-hydrogen bond, and then something's got to leave. We've got to get rid of one of these two atoms. They're both good leaving groups. So really, we should draw two different products of this reaction. One where the chlorine leaves, one where the bromine leaves. And we can have a conversation, we will have a conversation later about the difference between bromine and chlorine as a leaving group. One of them is better than the other. Not significantly, don't need to worry about that at this particular time. At this particular time, we're just really focused on the concept of stereospecificity and not the subtle difference between a bromine and a chlorine as a leaving group. So for our other elimination, that's going to take place right here in this spot. Because this is taking place between two chiral carbons, we are going to need to use a Newman projection to help us predict the products of this reaction. This is the reason, this right here is the reason that you have to learn how to draw Newman projections. So for this, we want to sight down the bond where the chemistry is happening. That means I'm going to sight in this direction right here. And when I'm looking in this direction, I have this isopropyl group sticking up. I'm just going to call that IPR for isopropyl. My bromine is down to the left. My chlorine is down to the right. On my back carbon, I have an ethyl group sticking down. I have a hydrogen up to the left. And I have a methyl group up to the right. So I have two leaving groups in this case. The leaving group, hydrogen, needs to be 180 degrees from a leaving group. And in this particular configuration, it is. So when the elimination reaction takes place in this spot, what we end up with, we'll have the methyl and the isopropyl cis to each other, and we'll have the ethyl and the bromine cis to each other. So let's go ahead and draw an ugly alkene over here. And I'm just going to start by drawing this, the methyl and the isopropyl on the same side of the double bond. And then on the other side of the double bond, I want to draw the ethyl and the bromine cis to each other. Now you do want to be a little bit careful. Make sure that you get the ethyl in the right spot. Should it be on the left-hand carbon? Should it be on the right-hand carbon? If you're looking at the Newman projection, you can see that the ethyl is on the back carbon of the Newman projection, and so is the methyl, which means that they need to go onto the same carbon in your alkene. And the bromine and the isopropyl group, they're connected to the same carbon, so they need to be connected to each other, like that. Now, don't forget that we do have this other leaving group as well, and we can rotate this molecule so that the hydrogen and the bromine are 180 degrees from each other. So let's go ahead and do conformation. And in this conformation, I'm going to leave the back carbon alone, so I'm not going to change the positioning of the back carbon. I'm going to rotate the front carbon 120 degrees clockwise. So that means it's going to have the bromine over here, the chlorine up here, and the isopropyl group down here. And if I do that, I'm going to eliminate in this spot. Let's highlight those guys. I'm going to eliminate right here. So that means my methyl and chlorine are going to be cis to each other. So here's product number 4. The methyl and the chlorine are cis to each other. And the ethyl and the isopropyl are cis to each other. Make sure that you got the ethyl and the methyl on the same carbon, like that. And then you could, if you wanted to, you could clean those up and make them look prettier. So that's all pretty tricky. There's a lot of steps involved there. Remember that E2 stereospecificity, we have to worry about that only when we're forming a carbon-carbon double bond between two chiral carbons, or a cyclohexane, elimination taking place on a cyclohexane. So that's what we're going to look at next. This is a little bit more complicated when we're dealing with cyclic molecules. So it's the same sort of situation with a cyclic molecule. The halogen and the hydrogen that are being eliminated, they need to be anti to each other. In a cyclic molecule, that means that they need to be 180 degrees apart from each other. They need to be axial up and axial down relative to each other. So guess what that means? That means that in order for us to be looking at this reaction, we're going to need to draw chair conformations. So first thing that I'm going to do is turn this molecule into a chair. Actually, the first thing that I'm going to do is find my carbon with the leaving group and all of the carbon atoms that are attached to it. When we're doing elimination between two carbons that are in the ring like that, we need to worry about stereospecificity, and we need to draw ourselves a chair conformation. If we're doing an elimination between two carbons and one of them is not part of the ring, like this guy right here, then we can just do a regular standard elimination reaction. We don't have to worry about anything in this case, so we can just do our normal reaction. A base comes in, grabs a hydrogen, gets rid of the leaving group. That's going to give us a product that puts the alkene right here coming out of the ring. Don't forget, we didn't touch this carbon, so we don't change this guy's stereochemistry. So this is one of the products of the reaction that comes from elimination taking place right here. Now, in terms of elimination in this site or elimination in this site, because this is taking place between two ring carbons, this is also two ring carbons, two carbons in the ring, we need to use a chair conformation to help us predict what the structure might look like. So I'm going to sketch out a chair conformation. I'm going to sketch in all of the bonds. This is where it's so important that you know your axial, equatorial, etc., like that. Know how to set up chair conformation. And I'm going to erase these, all the notations on here to make it easier for us to transfer this line structure into a chair conformation. Now, again, In order for elimination to take place, the leaving group and the hydrogen need to be anti to each other. And on a chair conformation, that means that they both need to be in axial positions with one up and one down. Like anything like this is going to work. So what we want to do is begin by placing our leaving group, because that's going to be important. We want to place our leaving group into an appropriate spot on this chair conformation. For me personally, I always interpret a dashed bond as a down bond. So I'm gonna, that means I want my bromine in any one of these down spots on the ring. And because this is an elimination situation, I specifically want my bromine down axial. So I'm gonna go ahead and put the bromine right here. Now, you really get to do kind of what you want to do in terms of translating a line structure into a chair conformation, but sort of keep in mind your life is going to be a lot easier if you take that halogen and you immediately put it on an axial bond, either up or down, whatever you want to do. So on this carbon, we also have that methyl group right there. Let's go ahead and draw that in. And on the ring, the next few carbons, the next 4 carbons around the ring are just hydrogen atoms. So I'm going to go ahead and draw those guys in. That's 3 and that's 4. And then this carbon right here has got a methyl group on the wedge, and I always interpret a wedge bond as sticking up. So we're dealing with this position, methyl group sticking up, which means that there's a hydrogen, there's a dashed hydrogen here sticking down. So this carbon is this guy, and one possibility for elimination would be occurring in, I'm going to use a different color, occurring right here. That carbon is this guy right here. And this elimination can only take place if the bromine on the pink carbon and the hydrogen on the blue carbon are 180 degrees apart from each other, meaning that one would have to be axial down and the other would have to be axial up. And that's going to be impossible in this situation just because of the configuration of this molecule. The halogen, the leaving group, and the hydrogen are cis to each other, which means that they're never going to be in an axial up, axial down configuration. They're always either going to be both down or both up. So we cannot do elimination between these 2 carbons because the hydrogen can't get itself into the right place. It's not an option. So I'm going to erase that highlighting right there. Now let's consider the other direction. So the other direction would be elimination between these guys right here, and that would be elimination between our down bromine and the up hydrogen in that spot. That would put the double bond right here or right here if we're thinking about the line structure. So now that we know exactly where the double bond is going to go, we can go ahead and draw that structure as well. The double bond went here in this spot. We did not do anything to this carbon atom, so don't do anything to its stereochemistry. We did chemistry for both of these carbon atoms, put that double bond there. Putting the double bond on this carbon makes it achiral. Remember that a carbon cannot be chiral if it's part of a double bond. So the methyl group that used to be on a wedge is now just a straight-lined methyl group because this carbon is no longer chiral. Whew, that's a lot to think about. Let's practice it again. We've got this guy down here. So first of all, here is our carbon with the leaving group, and we could possibly be doing elimination in either one of these sites. Let's draw ourselves a chair conformation, and let's kind of sketch in our bonds. And I am going to start by putting my leaving group, OTS, in an axial position. It's on a dash, which I always interpret as down, so I'm going to go ahead and put my OTS in this down spot right there. And then as I go around the ring clockwise, all I have are a bunch of hydrogen atoms, and the only ones that really matter are the ones that are right next to my leaving group. This carbon atom here, this is where the methyl group is located. The methyl group is up, so I'm going to put the methyl group right here. In my interpretation, a wedge bond is always an up bond. and my hydrogen is down. So this hydrogen right here is down. So my carbon with the leaving group is this guy, and I could possibly do elimination here, and I could possibly do elimination here. If I do elimination in this position, I'm going to be eliminating the OTS axial down and the hydrogen that is axial up. That is going to be elimination taking place in these positions right here. That's going to give me a double bond in this spot, the methyl group still on the wedge because we haven't done any chemistry there. Now in terms of elimination between these carbons, not possible. Our methyl group is axial down and our hydrogen is equatorial down. The leaving group, the OTS, and the hydrogen are cis to each other. It's going to be impossible for them to both be axial. They will either both be down or they will both be up. So no reaction can take place in this direction in the ring. This is the only product that we can make. I know that this is a really tough topic. We've got two more examples. This says it's even more complicated with a cyclic molecule that has a tert-butyl group. Maybe that's not entirely true. I don't know. We'll see. So first of all, let's find our carbon with the leaving group, and let's find all of the carbons that are attached to it. And notice we've got one carbon atom here that's not part of the ring. So that means that this is going to be an easy one for us to draw. Let's do that one first. That's going to build our confidence. Elimination between these two carbon atoms right here, which puts the double bond in this spot right there. And then I'll erase that little dot because we've got that guy figured out. Now elimination in the other two positions, these are between two carbon atoms in a cyclohexane, which means that we need to use a chair conformation. So I'm going to sketch out that chair conformation, and then I always start by tracing in all of my bonds so that I don't have to be thinking about axial up, axial down. Now in the previous example, I would start this, the last few problems that we did, I would always start this by taking my leaving group and putting it on an axial bond, either up or down, because I know that that's what it needs to do. However, in this example, we have a tert-butyl group. Tert-butyl groups are super bulky and they always have to be equatorial. When you have a tert-butyl group on a ring, the ring is actually not capable of ring flipping anymore. Tert-butyl groups can never be in an axial position. They are forced to always be in an equatorial position, which means that this molecule can't ring flip. It can't experience different conformations. So because of that, this rule that the tert-butyl group has to be equatorial, I have got to start by drawing this tert-butyl group in an equatorial position. Again, I always like to interpret my wedges as being up bonds, so I am going to pick an up equatorial spot. That's this guy, or this guy, and I'm going to draw in that tert-butyl group in the up equatorial spot. And I'm going to put it right here, and I'm going to just write it as TBU. And the other spot on that carbon is a hydrogen. So now when I go clockwise around the ring, so that means my next position is right here, this carbon atom, which is this carbon atom, that guy has a methyl group sticking up and a chlorine sticking down. Methyl group sticking up and a chlorine sticking down. Now, put the brakes on everything. We have said that the tert-butyl group has to be equatorial because it doesn't fit in an axial position. And if the tert-butyl group has to be equatorial, look at where the chlorine is. Because the chlorine and the tert-butyl are trans to each other, if the tert-butyl is up equatorial, the chlorine is down equatorial, and the elimination reaction can only take place if our leaving group is on an axial bond. It has to be on an axial bond. For this molecule, the chlorine is never going to be on an axial bond. It's not allowed. It has to be on an equatorial bond, which means that it is impossible for us to get elimination in any direction. We cannot get elimination this way because the chlorine is equatorial. We can't get elimination this way because the chlorine is equatorial. Our only option is elimination outside of the ring in that particular position. So see, that wasn't too bad. We've got one more example. Oh, this one does look a little bit tricky because once again, we have two leaving groups. We've got the bromine as a leaving group and we also have OTS. Let's start by looking at problems, reactions that involve the bromine as the leaving group. So if we're treating bromine as the leaving group, here are the two options for elimination. Both of those are options that are occurring within the ring, which means we need a chair conformation to help us sort this out. And so I'm going to sketch out the chair conformation. And we have a tert-butyl group again, which is going to be locked into a position. So the first thing we need to do is draw in that tert-butyl group. Where does it go? The tert-butyl group has to be equatorial because it's too big to fit axial. This tert-butyl group is a wedge, which I like to interpret as down. So here are my down equatorial spots. I'm just going to put it over here. I always like to start drawing everything on the right-hand side. And then that other substituent on that carbon is a hydrogen. So there's this carbon right here. If we go clockwise around the ring, the next carbon atom is just a CH2. And then the next carbon atom, this is where we have our bromine. The bromine is on a wedge, which I interpret as being in the up position. So look, this is good because we've got an axial bromine, which means that it's capable of doing elimination. What's on, if we continue to go clockwise, what's on the next carbon? Here we have the OTS group, which is in a wedge position, which is down in my interpretation. So that's going to be right there. And look, that's also good. We've got another leaving group in an axial position. So this is fantastic. And I'll go ahead and fill these guys in. So like I said, I'm going to start by looking at the possible reactions when bromine is our leaving group. When bromine is our leaving group, we're looking at doing elimination between these two carbon atoms, and that could take place between our axial bromine and the axial hydrogen. So that would be reaction occurring right here, elimination taking place right there. So let's go ahead and draw that product. Almost maybe the hardest part is looking at that chair conformation and then knowing how to turn it into a line structure. But I'm just sort of using benchmarks, like if I'm doing my elimination right here, it's like between the tert-butyl and the OTS groups right there, not on one of those carbons. Okay, so for bromine, this is the only option that we get if bromine is our leaving group. We can't go this way because the bromine and the hydrogen are not opposite each other. So I'm going to see if I can erase those highlighters. And then let's consider possibilities where the OTS is our leaving group. So if the OTS is the leaving group, we are looking at elimination between these two carbons or between these two carbons. If we go this way, the elimination would take place between this hydrogen and the OTS. That would give us a double bond right here. That would give us, would look like, lost a methyl group on my tert-butyl. So this would be nothing happening to the bromine, and the elimination is taking place between these two carbons, which is not with the bromine carbon. So the double bond would go right there. It would probably be extra helpful to number the carbons. If we numbered the carbons, that would be extra helpful. And then, so that's this possibility. What about going in this direction? In this direction, we can't do an elimination because the OTS and the hydrogen are not opposite each other. One is down and the other is down. So that would mean that the only possible reaction for OTS as the leaving group would be going this way.